So hey, hello. My name is Martin Dvorak, and in my today's talk, I would like to give you an introduction to Explainable AI, and also I would like to introduce machine learning interpretability module from the H2O Driverless AI product. I am with H2O for almost 4 years, and I am with MLI team, where I am software engineer. And I work on the driverless AI product. Okay, so after I will, somehow scope my today's talk, and I will move towards why the explainability matters and why it's important to be interested in that. In the third part of the presentation, I will talk about how to build models responsibly, and that part is called what because that model that the models we are building is what will be explained later. And finally, in that last part, I will describe how we explain the model using H2O AI solution and which methods and algorithms we use. So today I will focus on explainable AI. However, explainable AI is just one aspect of something which is much broader, and that's responsible AI. So a part to that explainable AI, which aims to provide methods that explain models and help people to understand how the models make decisions. There is ethical AI, which somehow elaborates sociological aspects, fairness, for instance. There is secure AI aspect or secure aspect, which aims to help model creators to avoid creation, for instance, of vulnerable models. Compliance aspect of the responsible AI is important for any regulated industry like healthcare, insurance, finance, or government, for instance. Machine learning interpretability is devoted to the architecture of the models, so that you design the models, for instance, feature engineering, and you select the models in the way which allows subsequent interpretation and also explanation. And finally, there is that human-centered AI, which is focused on collaboration or synergy between humans and AI to build better and responsible models. And it ranges from insights into data sets to actual creation, for instance, of models using AutoML solutions, and so on and so forth. So explainable AI will be focus of today's talk, but I will touch most of these aspects. This really rough description of model creation process aims to explain where the explainability fits. So there is a problem in the real world. What we usually do, we try to capture data. We have a data set. We try to build as good data set as we can. And then model learns the data set, and we get a result, which might be explainable to some extent. And then there are explainability methods which aim to extract knowledge and wisdom from what that model found and explain how the model makes decisions on how it works to humans in a way which is comprehensible to humans. And by humans, in this case, I meant both producers and consumers of the models. So both the authors, which need to make sure that that model is good enough, and then consumers who may use it for decisions which are important or may have some consequences. As I said at the beginning, I will be talking about the driverless AI, which is our flagship product. Driverless AI is a product which is here to build basically models using AutoML. And it helps you in building of these models end to end. So from the data set and data set analysis through actual experiment and model creation and subsequent diagnostics and interpretability to deployment to production. So it's end-to-end thing, but I will be focused on that MLI tab, which you can see at the top. Because there are many disciplines in machine learning, my talk will be focused on tabular data. There will be a bit of NLP, which is unstructured, so structured data and just NLP. As I said, that explainability in this case will be in the context of models created by that AutoML, by a product, and it will be supervised machine learning. And finally, in that last section, I will be explaining what MLI module provides and how we explain our models. So why explainability matters? So this section is supposed to be a motivation and a problem statement. So before I start, there are basically two types of models, and I will be referring to them in this way. So there are glass box models which are explainable by nature, I would say. So you may think of some decision tree, for instance, or models that has some kind of introspection, and you see or you can understand directly how that model makes predictions. On the other hand, there are also black box models which may be much more complicated, and when this is not possible. So, as I mentioned, I have some examples, like for instance, as I mentioned, decision tree, linear models, or models which are monotonous, for instance, as a representation of these glass box models, and the black box model in this case might be a complex neural network, or it might be a stack ensemble which is formed by multiple different models. And in that case, in case of that black box model, there is no straightforward introspection, for instance. So you can see on the side that the motivation for this is that often what we need to do is that we need to balance in some way the actual performance of the model and also its interpretability. So it's kind of controversial because there are already interpretable models which are complex, which are, for instance, neural networks with specific architectures. But overall, this needs to be considered. And the explainability can help with that. So these are just two extreme cases. So what I mentioned here is that either we are working on exact explanations for approximate models, or we do approximate explanations for exact models, which is some kind of trade-off which I'm referring to and which I'm talking about. Another interesting aspect where explainability may help is multiplicity of good models. In case of linear models, there is usually one best model, but in case of machine learning models, which are more complex, you may get multiple models which have the same or similar objective metrics, and in that case, you need to make a decision which of these models you would like to use. And this is where that explainability can help. You can find out how these models use features, how they make the decisions, how these features interact with the prediction. So even if these models are the same, internally they can work, in completely different way. And this explainability can help you in this case. Another important aspect that I mentioned at the beginning of the presentation is the fairness and social aspects. And you don't want to build discriminatory models, probably. So again, explainability can help you to find out that your model discriminates some subjects or makes a decision which are affected by gender, age, ethnicity, and other things. Another topic that I also mentioned at the beginning is a trust in the model that you build. So you build a model, it works nicely on your data set or your training set, on your polished data, but in the wild, in the real world, it might be completely different. Like here you can see some out-of-range values. So again, explainability with methods that can help you to, try some out-of-range values, examine sensitivity of that model, do some kind of a debugging, can help you to really trust that model. And the same applies to consumers. Another aspect is the security that I mentioned. So you should understand your own model so that it's not vulnerable, so that it can be, somehow compromised by an attack. And there are two aspects in this case where explainability can help. There, you may, for instance, detect that that model was somehow compromised already. So there may be an attacker who is I mentioned here backdoors, watermarks, data poisoning, and similar methods. And on the other hand, you can analyze that model when it's ready. Like here I have, for instance, that adversarial examples when you are trying to find out which the sensitivity of the model, whether there are some predictions which can be easily flipped, and how stable is that model, and many other aspects. So this is also where that explainability may help. Regulated and controlled environments, that's pretty straightforward. Banking, insurance, healthcare, pharma, and government. So there are legal requirements on the models. So, for instance, earlier I mentioned that fairness and discriminatory models, or there are some legal requirements on specific metrics, or there are requirements on justification of decisions which are made by the models. So, in that case, again, explainability may help, or this is actually a condition to put that model into the production. So, to summarize that, explainability can help you to balance performance and interpretability, to make a decision when you have multiple models and you want to do some reasonable decision which model to use. They can help you to build fair models and models which are not discriminatory. They can help you to establish the trust so that you trust the model and the consumer of that model trusts it. You can prevent or detect some problems with the model which were compromised or hacked. And finally, it's mandatory condition in case you build models for regulated or controlled environments. So in this second part, I will just briefly describe how to build the models responsibly. And this is not really core of the presentation, but it's important. The reason why I added this here is that the Explainable AI is basically about somehow examining the existing model. But if you want to build a model which is responsible and interpretable, you need to start thinking about that from early beginning. So even from the explanatory data analysis and insights into the data, through thinking about transformations which will be used by feature engineering and the selection of models. And then in subsequent post-hoc analysis, which I have in here. Because in the end, there will be human who is usually domain expert, who understands the semantics of the data set, and who can identify the problems that machines usually cannot, because he understands semantically to what's in the data and what makes sense or what doesn't make sense. And this should be iterative process. So in every step you should try to do this. If you find a problem, you should iterate it once more and once more. So that's what motivation for this part. So I mentioned that I will be talking about the driverless AI. So in that, I would say, early stage of data analysis, there is a part of the product that can help you to really get these models explained to some extent. So in this case, we do typical explanatory data analysis with metrics which are usually used. And apart to that, there is a tool which is called AutoVis, which analyzes the data and can find problematic problems basically in the data set. So you can find out whether there are problems related to the distribution, whether there are outliers, whether there are some problems with the correlation or leaks and similar things. So that's one part which is there. Then I mentioned that you should think about the interpretability and explainability when you build the model. And what we have in driverless in the product is that here you can see 3 knobs, and that's the creation of the new model. So for easy and straightforward creation of the model, you can see that there is accuracy, there is a time, and there is also interpretability. And then interpretability knob controls what will be used. So if that knob is on 1, then there will be used all the possible feature transformation and feature engineering which is available, and it will use complex models and stacked ensembles and anything which is available. If you turn it to 10, then the transformation will be really decreased only to the things that are interpretable, and for instance, linear models or simple models which can be easily understood are used. So this is the way how you can do that balance. You can simply choose what level of the performance is okay for you and what level of the interpretability is desired. And finally, you get the model. So you have that what, and now we can talk, or we can finally deep dive into how to explain the models and what we do in that MLI module. And I would say that this is used in a driverless, but I will just briefly describe how these methods work, so it is applicable in general. And also, we support third-party models in driverless even through their predictions, for instance. So, there. So how that fits into this big picture. So this is that postdoc part, basically. This part when you, as a human, have a tools, you get some kind of a metrics, methods, and explanations, and you are trying to decide whether that model works as expected. This is how it works in driverless. So when you finish the experiment and you get the model, you can just start the interpretation, and it makes a choice of available methods which are compatible with that model, because we support both IID, we support time series, we support regression, classification problems. So the specific methods are used for the specific models, and by default is run just a small subset or the most important subset of the explainers, and you can choose what you want to get, basically. And in the end, you get a list of explanations which are somehow organized to tabs in this case. So this is an interpretation just from the terminology. So here you can see that what you get in the end when you run that interpretation, you get some summary, which is not visible here, which just provides a basic information, like the digest of what was done. Then there are model-related methods. Then there are surrogate models. I will be talking about them later. There is automatic reporting, which basically describes the process of the model creation and how it was, constructed. If that model has some LNLP aspect, so there is also NLP methods, and you can even plug your own explainers, because our solution is extensible. So you can get methods which analyze that model from many aspects. This is just a view of these explainers, as I mentioned. So explainer is pluggable and configurable component which explains the specific model. So as I said, by default, it's somehow activated for a specific model type. You can tune it with parameters, what exactly you want to get, and how should do these explanations. And you can choose what to run. So you can run some default set, you can run everything that we have, you can run just one particular explainer, and you can even plug yours. So that's it. And here in brief, so that it's more approachable, driverless is written in Python, so the explainer is simply Python class. You implement an interface, and you get an explainer. You deploy the explainer, and then it gets the data set, it gets the model, and thus it gets also the predict function. And when the runtime activates it, this is executed and creates a set of explanations typically. And explanations might be, for instance, feature importance. And these explanations might be serialized to representations. And by representations, I mean CSV, JSON, frame, like data table or pandas, and so on and so forth. So this is, that component which is plugged there. This is how we, built that solution ourselves, and this is how it's extensible. This is just a high-level overview of what we have there, and I just added here so that you see that we have tabular data, text data, explainers, time series explainers. Some of them are just build something, some of them are interactive. And as I said, explainers build explanations, so this is just raw data, which are then normalized and are available in some formats. So this is here, and everything is extensible. Now I will talk about some basic model understanding and how to basically start. when you get that list of or tiles with the explanations what you should do. So usually that approach that you use is that you want to understand how that model works from high-level perspective, like approximate behavior of that model. So that's the first step. Then when you understand, how the decisions are made, you go deeper. And for instance, in this case, I mentioned that you are interested in most important features. So you look into feature importance on a global level. And when you know the most important features, you choose, for instance, that most important one, and you are interested in how it behaves, like what's the interaction of that feature values with the prediction and how it interacts with others, and so on and so forth. Then you understand that global view, you go again deeper and you do some local analysis. And by that I mean that you have a data set and you have your favorite row in the data set and you understand, or it's interesting from some reason, so you can use it and do the same analysis on that row. So again, you are interested which features were used for the prediction and what were the interactions and how it worked in general. And this is, what you do, and you are trying to understand, what's happening in the model and find, for instance, some problematic parts of the data set or problems in that model. So you usually start with something like a decision tree. So hopefully it's slightly readable, but that's pretty straightforward. In nodes, there are features. On edges, there are values. You can control how deep should be that. And basically what you get is this explanation which describes, for instance, this is an explanation of a regression experiment. So the values are growing from left to right. So you can see which features contribute to the high values, which features are important when it's predicting low values. And you can get any path in the tree represented as a pseudocode, for instance, or Python. So that's the global view. And this is really a rough description of how that works, how that model works. I mentioned local explanations. So in this case, you choose row number 11. And for that row, you can see which features would be used for the prediction and, what the prediction would be. So in that case, you will find out, whether it makes sense again, as I said, or not. Once you understand, this from this perspective, you can continue to the most important features. So you know how they are used. For feature importance, we use multiple methods. If that's possible, we use introspection, some kind of introspection. For tree models, for instance, have some kind of introspection where we can find out which features are the most important. But there are also models where it's not possible. So we use some methods which can be used on any model. So I would like to mention Shapley values, which is a very nice technique. It's a method which was invented in the 50s. It's a game theory method actually, and it started to be used in a machine learning. What's nice about it is that it has solid mathematical background. It's basically, as I said, this is a game theory, so it is about a game, about some players and a contribution to some result. And there is a nice analogy with the machine learning because these players are features, basically, and then contribution is prediction. So that's, as I said, there is solid mathematical background. It's nice and it gives really results which make sense. However, there is a glitch. It's exponential in the number of coalitions which are calculated as a part of that method. So usually there needs to be some kind of approximation. So this is why I'm mentioning different techniques that we use to make it possible. So Shapley values are really important and we support them. So here I mentioned, for instance, kernel-SUP. And apart to that, we, for instance, do permutation-based feature importance, which is working in a way that basically by permutating the column, you find out whether that feature is important and how, in short, in really simplified way. So here you get the notion about what's important, which features really matter. So, and again, this is available both for the global and local scope. So in this case, there is a row and you can see which features were important for that particular row. Another method which completes nicely with the feature importance is loco. So this is just abbreviation for leave one covariate out. And in this case, what we do, we just, remove one feature basically, and we try to find out how important is that feature and what's the difference in predictions. and how much that feature contributes. So what you get a chart like this, which summarizes whether that feature was contributing on average like positively or negatively. And you should always look into this chart along with the feature importance. The reason is that you may have a feature which has really like, low contribution, like in this case, pay 1, and typically in the data set, that's the most important features. And what that means is that it basically contributes more or less both positively and negatively. And, that contribution simply is somehow, eliminated. So that's important. And then you can find really features that are contributing only in one way. And again, local explanation is available for that as well. I don't know how much this is readable, but this chart is, based on Shapley values that I mentioned earlier. And it basically combines what I was talking also earlier. So, what this shows is a contribution in the context of all features and how it behaves on whole data set. So on x-axis, I have that Shapley value. So here you can see that this is 0 contribution, that is that vertical line. And here are like positive contributions and negative contributions. On y-axis, there are feature names and features. And what you can see here on that row, that's basically the description of how that feature behaves. So what I can read from that first row is that in case of pay 1, and I have the thermometer on the right, which also explains that if the values are low value, they are green, and if they are of high value, they are red. So in this case, it means that most of the examples or rows are contributing here, this value, and they are of low value. And here you can see that, that average values are basically contributing the most. I was earlier talking about important features that contribute both positively and negatively. So in this case, in case of age, if there is that big cluster, it means that there are many examples that, can see the contribution is almost 0, but big values are contributing either positively or negatively. So with high age, it basically is like that. And here, in case of limit balance, you can see that high values, which is that red on the left, are contributing negatively, right? So it's exact opposite of that pay 1, for instance. So this chart can give you some comprehensive view on, how these features are used by the model and how their values are contributing, and you can better understand whether it makes sense. If someone is of high age, whether it makes sense that it contributes like positively or negatively, for instance, to the prediction. This is just a drill down view. So as I mentioned, there are some clusters, so it gives you an explanation of how the data are structured. So again, Shapley value is x-axis, and here are the values, so you can see whether there is a gap or whether it's continuous and how it behaves. Partial dependence plot is next step. So you know which features are the most important, and you want to find out whether there is an interaction between the feature value and the prediction, and you want to understand what type of that interaction is. So first, I would like to explain that on the ICE, which is individual conditional expectation. And what you do in this case, so you choose a dataset row and you choose a feature. So in this case, it would be the total day charge. And then what you do, you just replace that value in that row for that particular feature with values. So what we do here is that you put there 3, 6, 9, 12, and so on and so forth, and you always change that value to the prediction, which is this. This is the prediction, that gray line. Then, you change the value to the prediction. And after you use all these values that are called bins, you can see that here around 40, there is an interaction, so that prediction starts to grow, which again, you can think about, does it make sense? Does it make sense that with the growing number, there is some interaction, and does that interaction make sense? So this is what you can do for the individual row. And you can do the same for the whole data set. So you can take the whole data set, you take the feature, that column, and you set it to some value. You do the prediction, and you average it. And then you switch the value and do the same. And this is that yellow. So that's the PDP. This is just the global view for that ICE. So, as I said, if this is flat like this, there is no interaction. There is almost nothing is happening there. it can look like this. So you may have direct proportion, indirect proportion, and then you can think about, does it make sense? Does it interaction works or not? Or there might be something more wild, but still, this is something which gives you, notion about that. So that was PDP. As I mentioned earlier, Driverless also generates auto-report, which is summary of how the model was created. And there is a whole creation process from selection of the transformations in feature engineering through dataset selections and so on and so forth. There are also certain charts. I was talking about the PDP, which you can see in here. So when the model is built in Driverless, for instance, you can get this, where is a summary of the most important things. So that's that, I would say, that basic understanding of the model. So what I was talking about was that at the beginning we just, find out what's the approximate behavior, that we go through features which are most important, and we try to understand how they behave and how they interact with the predictions. So the next step would be surrogates. And surrogate models are used to explain, in particular, like black box models when there is no introspection. So sometimes there is no other option how to do that. Sometimes, they can bring interesting techniques how to explain the models. So what is the surrogate model? Surrogate model is an interpretable model which is trained on predictions of that original model, so not on the labels. So what I have here is that there is an original data set and labels, and you create a model using AutoML, or you create it yourself. What you can do then, you can just score that data set with your model, and you get the predictions. And then you train that interpretable model. I have some linear one or decision tree or whatever, and you can train it here, and you basically get the model which predicts the predictions of that original model, along with all the bias and all the problems which were there, basically. So surrogate model, once more, is a model trained on the predictions of the original model. And with that, there are some techniques, again, the same approach I was talking about earlier, but this time it's done on the surrogate model. So in this case, we even, for instance, provide the dashboard. So here on the upper right corner, you can see feature importance. PDP, we were talking about decision tree. So for instance, when I want to get the local explanation, I choose a row and I see everything side by side. In the left quadrant, in this upper left quadrant, there is a K-LIME, which we use to do local explanations with reason code, so we can explain in detail how the model was predicting in that particular row, for instance. So K-LIME, as I mentioned, is used for this purpose, and it's a combination of K-means and LIME, which is local interpretable model agnostic explanations. And what's that? So what we do, basically, we take the data set and we cluster that. And when we have clusters, within these clusters, we train linear model or explainable model, in our case GLM, and the examples which are within that cluster are weighted by the basically distance from the values we are explaining. So that's in brief, what's happening there. So, and what we get with that, as I said, this is a surrogate model. So we were explaining that prediction of the original model. So there is that LIME method prediction, that actual target, and an original method prediction. And what we get are reason codes. What's the reason code? Reason code is, which I have here, is explanation of the prediction. So for every feature and its value, you get how much it contributed to the actual prediction. So in this case, for instance, you can see that age, and that value 23, which was on that particular line, was contributed with this reason code. And there are features and values which are contributing positively and negatively. And again, you can see which feature and its value is contributing most and which less, and it helps you to understand the model. These reason codes are also used for the justification of certain decisions. So sometimes reason codes are used basically even from the legal reasons to explain why what something was approved or not approved. So that's even the tool for that. Model debugging is really interesting technique. I was talking about that surrogate is typically trained, or that surrogate we were using for the previous technique was trained on the predictions of the original model. In this case, we train the model not on the predictions, but on the error, basically on residuals. So we find out, like, what's the difference between the prediction and the label, and we do the training on that. And it's really, like, interesting, because basically, if you think about that, the decision tree, for instance, navigates you to the place where, the location when you have the highest error. Where I was talking also about the PD. So that interaction, if you have some interaction, you can think that certain features have a problem with the error, and so on and so forth. So there are these interesting aspects, and surrogates can be used for this method to understand better where your model is, like, not performing well. So again, and for this, we have a dashboard and everything, you can see side by side and understand that model. Yeah, same thing as for the, like, the normal surrogates. Text features. If your data set contains a column with the text data explainers, which can explain text features and their values, tokens are activated. So again, the approach is basically very similar. We have multiple methods how we explain these things. So the methods I was talking about earlier have tokens, for instance, included. If there is something which is specific, like feature importance, we have a couple of methods how we explain the feature importance in this case, or token importance in this case. So this is just, the dashboard I was, talking about earlier, and here you can see these green values are tokens and text features. So description is feature and TV is token. And you can see in the context of other features how that token contributed to the prediction. And it applies to all these things. So decision tree includes it as well. In PD, you can choose it. You can see that feature is also in here. So in the K-LIME. For the feature importance or token importance in particular, we have a couple of methods how we do that. One of the interesting methods that we use is NLP, vectorizer, and linear model. And what this explainer does, what we do TF-IDF. And basically, you can imagine that we get a data set, and in the columns, we have features, and you have these values. And we build linear model on top of that, and we predict the actual, labels. And the coefficients of that model give us the importance of the tokens. So this is what you can see here. So there is both, again, global explanation and also local explanation. So in this case, for a text, which was as a value of that feature, you can see which tokens contributed positively, which tokens contributed negatively, and so on and so forth. So this is how to understand how tokens are, influencing the prediction. Then there is an NLP tokenizer where we use IDF and TF-IDF, and this is pretty straightforward. Here you can see the tokens, and here you can see, the local explanation, sorry. We have NLP loco also for NLP, and it works in the same way. So imagine that you have that text column, and what we do, we know what are the most important tokens, and what we do in case of, global explanation, we remove that token, and we do prediction, and then we just do predict that with the token. And this is the way how we find out whether that particular token is influencing the prediction and how much. So again, this is leave one covariate out, and in this case, that covariate is the value. So we erase that token from that text. So that's the local, and again, the analogy to that normal local I was talking about earlier is there. And this is what you can again see, in this case, excellent is contributing positively. It will be probably some review, positive, negative review, right? And dog negatively. So yeah, so that's what you can get with the NLP loco. We have also NLP PDIs, but in this case, again, you can see side by side how that row or that token behaves in global and local case, if it's there or not there. So it's basically different visualization of loco. Yeah. Now I would like to switch to fairness. So I mentioned the fairness earlier, and for that we have disparate impact analysis. So what this tool does, so imagine that you have a data set, and in the data set you have features like gender, so male, female. You have education, for instance, or you have marriage status. And what you do at the beginning, before the training, you probably remove these features because you don't want to introduce some kind of unfair behavior of that model. So you remove that. And when you get that model in the end, you can use this tool to find out whether you don't have, for instance, some kind of a leak, that that information is actually there, or whether that model is performing well in all the groups. And by groups, I mean, for instance, that when you have the model, you take the data set, and because you have that feature, which wasn't used for the training, so you just take the data set which was for men, and you do a couple of metrics, like accuracy and similar metrics. We have many of these. And you do the same for women. And then you compare. And if there is big discrepancy, for instance, in accuracy, in error, or in other metrics, you have a problem. Or you may find out that you actually don't have enough data. So you can do this for, I mentioned the gender. Education is the same thing. So you just take rows which were for university, for high school, and so on and so forth, and you do you calculate these metrics within these groups, and then you compare it side by side. And this is not much visible here, but there are some kind of a threshold. So there might be some discrepancy, but if that discrepancy is too big between the groups, you know that, for instance, you don't have enough data for other education or certain group. So what you want to basically achieve is that there is no leak, and that these groups are treated more or less equally, and there is not big discrepancy. And this is why it's disparate impact analysis. So in short, this is how that works. Model debugging is more advanced thing, and that's interactive tool for analysis of the model. So this is kind of a Swiss knife. It's interactive application. So what you can see here, you basically load any data set and you load the model. And then what you can do, you can filter the data set in any way using any feature. You have some visualization how it looks like for any feature. So you can filter the data set. You can transform it. So for instance, you can set it to some particular value like whole column, some value here. You can permutate, you can randomize it. So you do some kind of a transformation, and then you rescore that. So this is some kind of loop. So you filter, transform, score, filter, transform, score, and you do these things. And with this, you can do just some kind of a global analysis manually. So for instance, you can do PD or ICE. You can set the column to some value, do the score, set it to another value, to the score, set another value to the score, and you can then follow whether these predictions were changing. This is here in the right. So it can be, there might be some interaction. So you can put there out of range values, something crazy, something that model doesn't expect. So some age negative value or some high value. Or you can use even invalid values to find out whether that model will alive, or whether it will give some meaningful prediction, or whether it will not flip the prediction, and so on and so forth. So you can do DIA, as I was talking about the groups. So you can filter, for instance, divorced man older than 50 years, right? Something like that. And you can do that analysis within this group. So that's it. And you can do it globally, and you can just filter out one row, and then do these transformations there. So that's what if analysis, and that can be used for many things and for testing of the model, basically debugging stuff. What if I change this? What happens? And if it's not enough, if this interactive tool is not enough, we have that bring your explainer functionality, as I mentioned. So you can just upload that explainer that you implement, and it takes, it immediately becomes part of our framework, and it's activated whenever it's compatible, and its explanations are available here. So as other explanations. So in general, how that works. We have even online editor, so you upload it, you can modify it here, you can even debug it, you have logs, and you can work with that. So that's support for the development of these things. So as I mentioned, this concept is brinker or explainer. I was describing this earlier. So this is just Python class, you implement that class. Important thing is that if you use our helper classes or API, and if you normalize the output of that explainer, so it may be feature importance, some specific JSON format, you get all visualization. So you get these interactive charts, screenshots. I was showing the screenshots earlier. So you get basically full-fledged explainer also with the visualization. So here an example is that Loco. So Loco calculates a normalized JSON. It's visualized in UI. You can do global local explanations, and you can get it as a JSON data table, CSV, for instance. And this is just for free, it's converted by that. So yeah, so explainers, explanations, representations, as I mentioned, and we have like visualizations by bar charts, PD, DT, and similar like things. That explainer, really briefly, is simple. You just implement, as I said, a class. You give it a name, description. You declare that it supports regression, for instance, or multinomial. You can declare which are the dependencies, and then you just implement setup, which is some kind of initialization, and explain. And explain gets a data set, labels, and the model is injected, so you can see here there is just predict method. So you have all the data, you have predict method, and it's up to you what you want to do. And this is the way, this is actually like a valid explainer. This just scores the data set and provides the predictions for the download. And we have examples and templates. So with the templates, you get basically a skeleton of that explainer for these types that I mentioned, like Markdown report and other types. And you can just fill in that explain method, and that's it. So you don't have to cope with the rest or with some boilerplate code. So both templates and examples are publicly available. Yeah, and that's it. Here are some takeaways. What I wanted to today present is that explainability matters, that there is a concept of responsible AI, which is like a holistic view on how to build models responsibly. There is something like multiplicity of good models where explainability may help. H2O Driverless AI provides interpretability and explainability. You should control that end to end. You should think about it from the beginning where you are building a new model. You should prefer models which were built responsibly. You should test your model like any other software, like using these debugging tools. You should use synergy of the local and global techniques. And finally, Shapley values are really great. Use them. So that's it. Thank you.